Today's lecture is about curve sketching, and this is really bringing together everything we've talked about in chapter 3 about how the derivative, both first and second derivative, affect how the shape of a graph looks. Now, I know that we have graphing calculators and we can look at all of these things, but this is really about the idea of bringing together all of those things we've learned about derivatives and figuring out what the graph looks like. So you can check with your calculator, but this way we know a lot more about what's actually happening with the function. And that being said, this is a topic which takes a lot of time, and so although this particular screencast may not be that terribly long, the material is going to cover a couple of class days. So just keep working at it. It'll take a little while, but you can do it. All right. First, I just wanted to summarize the things we've talked about with derivative tests because we've looked at them in different ways, and I just wanted to put them all together here. So as you go, you should fill these in on your handout. I left some blanks for you to fill stuff in. So the increasing-decreasing test says that if f prime is positive on an interval, then f is increasing on the interval. We've looked at this in different ways, of course. So if we know the formula for f prime, then we're going to use critical numbers. Remember, that's where the derivative is 0 or does not exist. We're going to use those to label the number line. We're going to break it up into subintervals, and then we're going to check in each of the subintervals to see whether the derivative f prime is positive or negative. And we labeled the subinterval with positive or negative for f prime, and then we also labeled the subintervals with increasing or decreasing for f, depending on which we have, positive or negative for f prime. If we have the graph of f prime instead of the formula, then we're looking for where the graph is positive, in other words, where it is above the x-axis. On the other hand, if f prime is negative, less than 0 on the interval, then f is decreasing on that interval. So if we know the formula, we do the same thing. We use the critical numbers where f prime is 0 or does not exist to make a number line. We test in the subintervals to see if f prime is positive or negative. We label the subintervals with increasing or decreasing. And if we have the graph of f prime, we want to know where f prime is negative. So that means we're looking for where the graph is below the x-axis. All right, first derivative test for critical points. So if C is a critical point, then the first derivative test, and the way it's different from increasing and decreasing, so it uses the same information from increasing and decreasing, just labels places where direction changes with local max or local min. So if f prime changes from positive to negative, then C is a local max. So if we know the formula for f prime, we do the same things we did for the increasing-decreasing test. We use the critical numbers to make a number line. We label the subintervals with positive or negative for f prime. We label the subintervals with increasing or decreasing. And then we look for where f prime changes from positive to negative, or where f changes from increasing to decreasing. And that's where we will have a local max. If we have the graph of f prime, we're looking for where f prime switches from positive to negative, so that's from above the x-axis to below the x-axis. Going the other direction, looking at local mins, if f prime changes from negative to positive at a critical number, a critical point, then C is a local min. So we can use the increasing-decreasing test information, but again, we are just labeling local max and local mins as well. So if we know the formula for f prime, we find critical numbers to label the number line. We label the subintervals with positive or negative for f prime, and then increasing or decreasing for f. And then for a local min, we're looking for where f prime changes from negative to positive, or where f changes from decreasing to increasing. And if we have the graph of f prime, we're looking for where f prime switches from negative to positive, so that's from below the x-axis to above the x-axis. Now we get to the second derivative test. The second derivative test is not as relevant for our graphing efforts, But it is a useful test to know if we want to fairly quickly figure out if a critical point for f is a local max or local min. And we can do that just by evaluating the second derivative. So if the second derivative is easy to compute, this could be a really fast way to figure out if we have a local max or local min. So if we have a critical point of f and f double prime exists there, then if the second derivative is positive, c is a local min. And if f double prime is negative, the second derivative is negative, then c is a local max. And if f double prime, the second derivative is 0 there, use the first derivative test. Now, concavity test. This is about concave up and concave down. And the concavity test tells us if the second derivative is positive on an interval, then f is concave up on the interval. So if we know the formula for the second derivative, we use the numbers where the second derivative is 0 to make a number line. We label subintervals with positive or negative for the second derivative. We label the subintervals with concave up or concave down for f. If we know the graph of f prime, we are looking for where the graph of f prime is increasing. Going the other direction for concave down, if the second derivative is negative on the interval, then f is concave down on the interval. Same process for if we know the formula for the second derivative. We use the numbers where the second derivative is 0 to make the number line. We label the subintervals with positive or negative for the second derivative. We label those subintervals with concave up or concave down for f. For the graph of f prime, if that's what we know, we look for the graph of f prime, where the graph of f prime is decreasing, and then f will be concave down. And finally, inflection points. So if the second derivative is 0, and the second derivative is changing from positive to negative, or negative to positive at c, in other words, it is changing sign, then there's an inflection point on the graph of f at x equals c. So if we know the formula for the second derivative, we use the numbers where the second derivative is 0 to make a number line. We label the subintervals with concave up and concave down, and then we look for where the concavity changes, either from up to down or down to up. If we know the graph of f prime, so if we know the graph of the derivative, we look for where the graph of f prime changes from increasing to decreasing, or decreasing to increasing, or in other words, we look for any local max or min of the first derivative. So that gets us through the summary of the things we have done so far, and we are ready to move on to our key idea, which is in the book 3.5.1, and these are the steps that we are going to go through in order to bring together the graph of a function. So in our curve sketching section here, key idea 3.5.1, the first thing we're going to do is we're going to determine the domain of f. We go ahead and assume the domain is the entire real line, and then we find restrictions, such as where there's a 0 in the denominator or where negatives would be under a radical. So for example, if we had the function f of x equal e to the x over square root of x minus 2, we go ahead and assume that the domain is all real numbers, and then we look for problems. Well, clearly we're going to have a problem with a 0 in the denominator because we have a denominator to look at. So we cannot have x equal 2, but we also don't want anything negative underneath the square root. So we need x minus 2, which is what's under the square root there, to be positive. In other words, we need x greater than 2, and that gives us the interval 2 to the infinity. So if we were graphing this function, we would only graph it for x equal 2 and onward to the right. We would ignore everything else to the left. The next thing we do is we find critical values of f. Again, that is where the derivative is 0 or does not exist. We find x values for possible inflection points of f. So that's going to be where the second derivative is 0. Then we also want to know about any vertical asymptotes of the function. For that, we are going to compute limits where there's a 0 in the denominator. So for example, if we look at f of x equal x plus 1 over the quantity x minus 2 times the quantity x plus 3, that's going to have two vertical asymptotes, one at x equal 2, because that would make x minus 2 in the denominator 0, and one at x equal negative 3, because that would make x plus 3 0 in the denominator. Now to see what the graph of f does on either side of those x values, we're going to use limits. So we're going to look first at the limit as x approaches 2 from the left, so that's 2 from below, the values of x are less than 2, of x plus 1 over x minus 2 times x plus 3. Now because we get a 0 in the denominator but not in the numerator, we expect there to be infinite behavior. The question is just a matter of, is it positive infinity or negative infinity? So we're going to think about a number that is really close to 2, but just a little less than 2. So think about, say, 1.9, or 1.99 is even better. In the numerator, if we plugged in 1.9, that would be positive. In the denominator, if we plug in 1.9 to x minus 2, that would give us something less than 0. We get 1.9 minus 2 would be negative 0.1. So that's going to be negative. If we plug into x plus 3, that's going to be positive. So we have positive over negative times positive. So overall, that is negative. So this limit is negative infinity. In a similar way, we look at x approaching 2 from above. So again, we're still expecting that infinite behavior. Now we need to check will be positive or negative infinity. So we're going to think about plugging in 2.1 or 2.01. If we plug that into the numerator, that would be positive. If we plug into x minus 2 in the denominator, that would be positive because the number is a little bit bigger than 2. If we plug into x plus 3, that would also be positive. So we get positive over positive times positive, which overall is positive. So we get positive infinity. And then looking at x approaching negative 3 from below, we're going to pick a number close to negative 3, but below it on the number line. So for example, negative 3.1. If we plug that into the numerator, that would give us negative. If we plug into the denominator, we're going to get negative when we plug into x minus 2. And then when we plug into the denominator at x plus 3, that would give us something negative as well. So we're talking about, say, negative 3.1. So negative 3.1 plus 3 would be negative 0.1. So we have negative over negative times negative. So overall, we end up with negative infinity. Likewise, when we look at x approaching negative 3 from above, we want a number that is close to negative 3, but just a little bit above it on the number line. So something like negative 2.9. When we plug into the numerator, that's going to give us negative. When we plug into the denominator in x minus 2, that's going to give us negative. And then when we plug into x plus 3, if we have negative 2.9 plus 3, that's going to give us positive 0.1, so that will be positive. So overall, we get negative in the numerator, negative times positive, which is negative in the denominator. So we have negative over negative gives us positive infinity in this case. All of that is useful information for what the graph will look like. Moving on to our next step, we determine end behavior by computing limits as x goes to infinity and x goes to negative infinity, and this may include some horizontal asymptotes. So, first example we're going to look at here, we're going to look at the limit as x goes to infinity of sine of x over x, which will be 0. Here's why. As we look at sine of x, that's always going to stay between positive 1 or negative 1. That's what the graph does. It can go up to positive 1, go down to negative 1. X is getting really, really big as x goes to infinity. So when we have something between positive 1 and negative 1 and we divide by a really big number, it's going to get smaller and smaller and smaller. Even though it's going back and forth between positive and negative, it's still getting smaller and smaller and smaller. So the limit is 0, which means that function, sine x over x, has a horizontal asymptote y equals 0. Another example, if we look at x going to negative infinity of 2 plus cosine x over x. Well, the 2 is not going to change no matter what happens with x. So we're going to focus on cosine x over x. And it's the same idea as what happened in our previous example. Cosine x is always between positive 1 and negative 1. So when x goes to negative infinity, that's getting really, really big and negative. So in the numerator, we've got something that's stuck between 1 and negative 1, getting divided by something really, really, really big and negative. So overall, that quotient, that ratio there is getting smaller and smaller and smaller, getting closer and closer to 0. So we get 2 plus 0 is 2. So that function, 2 plus cosine x over x, has a horizontal asymptote at y equal 2. Also, just as a reminder, we've talked about this before previously in the class, limit as x approaches infinity. If we have x over some positive power, so like 1 over x to the third power, we would get 0. So f of x equal 1 over x to positive power, whatever that positive power is, would have a horizontal asymptote at y equals 0. We also are interested in what happens with polynomials in terms of end behavior, meaning as x goes to infinity or negative infinity. So think about a polynomial. Always, 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 what happens with the polynomial when x goes to infinity or negative infinity depends on the leading term. The biggest term, we've got the largest power of x. So for example, if we had x going to infinity of, say, x squared, that is our biggest power of x. What's going to happen with that? Well, x squared will get really big, so that will go to infinity. Well, what if we were looking at x going to negative infinity of x squared? Well, a negative number squared will be positive and big, so we would get positive infinity as well. So those are the sorts of things you want to look at. Also pay attention to coefficients. They could be positive or negative, and that could affect what happens with the end behavior, whether we get a positive or negative. And then lastly, in this step, just a reminder of what happens if we have a rational function. We have a polynomial over a polynomial. That always comes down to what happens with the leading terms. What is the biggest power we have? And we compare the biggest powers. We could get 0, we could get infinity or minus infinity. We could get a ratio of the leading coefficients if the powers are exactly the same for those leading terms. Okay, now on to the last bits, our last 2 steps, I think. This next step is really important for organizing all of our information. You're going to create a number line that includes all critical values, all possible inflection points, and any vertical asymptotes that are there. And in each subinterval that we get on the number line that way, we're going to determine whether f is increasing or decreasing. We're going to determine whether f is concave up or concave down. And we're going to label the number line that way. And we're also going to label the way the graph should look. For example, if we were increasing in concave up, it should go that direction. If we were increasing in concave, oops, that was wrong. If it's increasing in concave down, it's going to go like that. If it's increasing in concave up, it's going to go like this, and so on. And we'll see that in examples. Step 7 is to bring all of this information together and sketch the graph, including the point of the graph for any critical values. So that means if we have our x value, we are going to find the y value for that point, and we're going to plot that point. Any inflection points, we are going to plot those points. We're going to take the x value, plug into the function, plot both points, the x and y coordinates. We're going to sketch any vertical asymptotes. We're going to sketch any horizontal asymptotes, which we've found in the end behavior step as well. So those are all of our steps. As you can tell, that's going to be a lot for us to bring together. And I'm going to do that with 8 different examples. And you can see why this would take more than one class period to get through a bunch of examples. So here are the examples I'm going to do. I'm going to post these as pencasts in Blackboard so that you can listen and watch as I write out these examples. And I'm going to go through all of the steps, and you can fill these in on your handouts as you go. So, curve sketching, big ideas, bringing a lot of things together, but we'll see how they all come together in the examples.